Welcome to the next video in the Crystal Clear Electronics 2 curriculum. We will focus on control engineering, and within that, we will look in depth at regulation. The chapter was written by Gergő Herangli and proofread by Ádám Szabó. Our main presenter today will be Szabolcs Pályer, who you may already know from previous videos.
In this chapter, which is divided into 4 videos, we will look at different types of regulators. In the first, we will discuss systems and models. In the second, we will discuss the concepts of control and regulation. The third video will cover the theoretical basis and specific controllers. And in the last part, we'll look at some modern control applications. My partner today will be Előd Kovács. I had the pleasure of teaching him for 4 years. Előd graduated in advanced physics and mathematics with excellent results. He has also participated in the Crystal Clear Electronics summer camps and study groups. Now, let's get down to business, so sit at a table. Let's begin with a concise definition and then break it down into easily understandable parts. Control theory is the field of engineering concerned with the theoretical principles and practical implementation of autonomous control, of which control is a subfield. Regulation is a control process in which intervention is based on the difference between the actual and specified values of the characteristic to be controlled. Control factors can be temperature, water level, or anything you want to regulate. So Előd, how would you tell an enthusiastic person what regulation is?
If I were to say it word by word, I'm not sure they would understand it immediately. To put it simply, I would say that regulation is a way of maintaining a physical characteristic at a desired level.
I think an example might help to make it easier to understand. The ideal temperature for us is 23 degrees centigrade, so we want to maintain this in the flat. If the temperature falls below the specified value, the heating will be switched on and then switched off as soon as the desired value is reached. If the house gets too hot, the air conditioner will switch on and cool the indoor temperature down to the ideal value. This is a very oversimplified example of control theory, as our devices would then be constantly switching on and off.
I hope you like this simplified example, because we will use more scientific language from now on. Let's start by learning a few terms to describe control systems.
In control theory, we can classify solutions according to a number of principles that help us find the control for a given task. First, we define the concept of a system, for which we have a figure. The system is a well-defined part of the world that is interesting to us for some reason. This is why we want to observe and control it. Very generally, we can say that a system can have inputs, states, and outputs. In most cases, a system is an abstraction. A great example of a system is a car. The possible inputs of a car are accelerator, brake pedal, steering wheel, handbrake, fuel. An imaginary possible set of states is the engine speed, temperature, gear, orientation of the wheels, in other words, which way the steering wheel is turned. The output can be the vehicle speed, acceleration, direction of travel.
The concept of a system is very general and quite difficult to grasp, so it is necessary to introduce a new term, the model. This is a simplification of the system, which is good if it contains all the properties that are important to us but is expressed as simply as possible in the form of mathematical equations. I would very much like to emphasize simplicity, as it is relatively easy to describe complex models mathematically, but managing and integrating them into working systems can require considerable resources. Therefore, when we model, we extend and complicate the model only as far as it is absolutely necessary. The inputs and the outputs of the model can have any number of signals, by which we mean the information carried out by a physical quantity that is useful to us. These are application specific, but we often come across voltage, current, or even the temperature mentioned earlier as inputs and outputs of the model. Each signal represents a well-defined quantity. To return to the car example above, for example, one input is the angle of the accelerator pedal, the output is the speed of the vehicle. There are many types of models, each of which highlights an important mathematical property. Mathematics is a very diverse science, so we can group models according to many different criteria.
The first aspect is the time progression, which distinguishes a model as continuous time or discrete time. Let's illustrate this with a figure. In the case of the continuous time model, we can say that between any 2 points of the signal curve, all the values exist continuously. The continuous time model works with continuous time signals. In a discrete time model, the signals only change at certain times, but their value at that time can be anything. The word discrete in this case refers to time. Also known as sampled models, this term is well known from the operation of analog to digital converters. At the level of the model, a similar thing happens. In the example, the blue signal is sampled every second and held for 1 second. Another aspect could be distinguishing between static and dynamic models. A model is called static when its output signals are determined only and exclusively by the function of its input signals at that moment. In the case where the value of the output signals also depends on the past, we speak of a dynamic model. Take, for example, a resistor divider with a voltage applied to its input and a voltage divider output. This is a static system since the output voltage depends only and exclusively on the instantaneous value of the input voltage. In an RC circuit, where a capacitor is charged through a resistor, we are already talking about a dynamic system since the change in the input voltage does not immediately appear at the output.
Another grouping aspect could be linearity. To determine this property, it is already necessary to see the specific mathematical model that models the part of the system that is important to us. We can say that a system is linear if each state variable is first order, that is only the first power is included, and between them there is only addition and multiplication by constants. In other words, a simple single input, single output model is linear if there is a constant ratio between its input and output with a possible offset. This means that if the input signal is x and the output signal is y, then y equals a times x plus b, where a and b are constant numbers and a is not 0. When functions appear, which are variables or state variables, products, angular functions, or even powers, we are talking about a nonlinear model. A more advanced mathematical background is required to understand this properly, which will not be further discussed in the curriculum. Fortunately, in reality, most phenomena and systems can be estimated by linear models. As we will see in the designing of the regulator, sometimes controllers can be well adjusted without a precise knowledge of the model.
In the following video, we will continue with open loop and closed loop control. Stay tuned. Bye bye.
Bye.